Right now, a real asteroid is being tracked by NASA as it moves through the inner solar system on a path that brings it uncomfortably close to the Earth and Moon system. And the energy locked inside this object is enough to level an entire city in seconds. This is not a drill. This is not a distant theoretical scenario pulled from a science fiction plot. The asteroid has a name, a calculated orbit, a confirmed close approach date, and a kinetic energy signature that planetary defense scientists take very seriously. The object is called 2026 JH2, and if you have not heard of it, that is actually a large part of the problem. It was only discovered on May 10, 2026, just 8 days before its closest approach to Earth. 8 days. That is, the entire window humanity had between first detecting this object and watching it sweep through the Earth and Moon system at a speed of over 9 kilometers. Every single second. The question is not whether this particular rock is going to hit us, because it is not. NASA has confirmed that with certainty. The real question is what this event reveals about our planet's vulnerability to objects we have not seen yet, the ones still lurking out in the darkness of the inner solar system, completely invisible to every telescope currently scanning the sky. And the answer to that question is genuinely unsettling. To understand why this flyby matters so much more than the headline suggests, you have to understand what an object like 2026 JH2 actually carries with it. Not just its size, but its energy. Not just its distance, but what that distance actually means in human terms. When planetary scientists look at a rock like this, they do not just see a small asteroid making a pass. They see the equivalent of hundreds of thousands of tons of TNT moving through cislunar space at a velocity most people cannot intuitively process. They see a potential airburst that, in the wrong scenario, could shatter windows across an entire metropolitan area, crush structures, injure thousands of people, and leave a zone of destruction that would take years to recover from. And they are reminded, once again, that Earth has no guarantee of safety from objects in this size range. The planetary defense community has spent decades building survey networks, developing deflection technologies, and running simulations. The DART mission proved that we can push an asteroid off course. The science is real, and the tools are being built. But none of that matters if we do not see an object coming until it is 8 days away. There is no mission you can design, launch, and execute in 8 days. There is no deflection strategy that works on that timescale. You are left with one option, and that option is evacuation. That is the honest reality that 2026 JH2 has just reminded the entire world of. And it is worth sitting with that for a moment before we go any further. Because this is not a story about an asteroid that missed us. It is a story about a system that nearly had no time to respond at all, and about what that means for every object out there we have not found yet. So let us start from the very beginning, from the moment this rock was first spotted as a faint smear of light against the deep sky, and trace its journey all the way to the moment it sweeps past our world at a distance that places it well inside the orbit of our own moon. The asteroid 2026 JH2 was discovered on May 10, 2026, by the Mount Lemmon Survey, one of the most active ground-based asteroid detection programs operating in the world. The survey uses a 1.5-meter Cassegrain reflector telescope located in Tucson, Arizona, and it is optimized specifically for wide-field detection of faint solar system objects. When the object was first imaged, it appeared at an apparent magnitude of 21, which is far too dim to be seen with the naked eye and even too faint for most casual telescopic observers. It showed up as a slowly moving point of light against the fixed stars, the classic signature of a nearby solar system object. It was initially given the provisional designation CLU-1Q2 before the Minor Planet Center formally catalogued it as 2026 JH2. Follow-up tracking was quickly organized using facilities including the Farpoint Observatory, and within just 2 days of observation, astronomers had enough data to calculate a preliminary orbital solution. What that solution revealed is what elevated this object from a routine discovery to an object of genuine scientific and civil interest. 2026 JH2 belongs to a population of asteroids known as Apollo-type, near-Earth objects. Apollo asteroids follow orbits that cross the orbital path of Earth around the Sun, meaning they periodically enter the neighborhood of our planet. The orbital parameters, calculated for 2026 JH2, tell a vivid story about where this rock spends its time and why it ends up so close to us. Its semi-major axis sits at 2.43 astronomical units from the Sun. Its orbit is highly elongated with an eccentricity of 0.584, which means the path it traces through the solar system is far from circular. At its closest point to the Sun, its perihelion, the asteroid dips to just 1.01 astronomical units, placing it right in the neighborhood of Earth. At its farthest point, its aphelion, it reaches out to 3.85 astronomical units, stretching toward the outer edges of the main asteroid belt near Jupiter. It also orbits at an inclination of 6.2 degrees relative to the plane of the ecliptic, meaning it cuts across that plane at a slight angle rather than circling entirely within it. The physical nature of the asteroid is derived from what is called its absolute magnitude, which is a measure of how bright it would appear under standardized conditions. The absolute magnitude of 2026 JH2 is 26.1. To translate that into a physical size, planetary scientists supply what they know about how much sunlight different types of asteroid surfaces reflect, a quantity known as albedo. If this asteroid is a highly reflective silicate-rich S-type body with an albedo of 0.25, its diameter would be approximately 16 meters. If it turns out to be a darker carbonaceous C-type body with a lower albedo of 0.05, its diameter could reach up to 35 meters. The most likely median estimate places its size around 25 meters in diameter. To help your brain build a picture of that, a 25-meter asteroid is roughly the size of a large passenger aircraft or a basketball court. It is not a mountain. It is not the kind of object that would end civilization or trigger a mass extinction event. But what it lacks in sheer geological scale, it more than compensates for in velocity, density, and kinetic energy. Assuming that median 25-meter size and a typical stony asteroid bulk density somewhere between 2,500 and 3,000 kilograms per cubic meter, the estimated mass of 2026 JH2 falls between 20.4 million and 24.5 million kilograms. Now multiply that mass by its approach velocity of 9.17 kilometers per second, run the kinetic energy calculation, and you arrive at a figure between 8.6 and 10.3 times 10 to the power of 14 joules. That is a number that requires context to feel real, and that context is coming. The close approach of 2026 JH2 to the Earth and Moon system is a precisely choreographed event that planetary scientists have calculated with remarkable accuracy. The asteroid does not simply streak past in a single moment. Its passage involves a timed sequence of gravitational encounters that gives astronomers multiple windows to study it. The timeline begins on May 18, 2026, when the asteroid makes its closest pass by the Moon at a distance of approximately 423,000 kilometers. That happens at 1851 Coordinated Universal Time. Then, less than 3 hours later, at 21:23 Coordinated Universal Time, the asteroid reaches its closest point to Earth, a distance of roughly 91,000 to 91,300 kilometers from our planet's surface. To put that distance into the perspective that actually matters here, the average distance between the Earth and the Moon is about 384,400 kilometers. This asteroid is passing Earth at just 24% of that distance. It's close to us than the Moon is, and it is doing so at more than 9 kilometers per second. The geometry of this encounter is worth visualizing clearly. The asteroid passes through what is called the Earth Hill sphere, which is the region of space around our planet where Earth's gravity dominates over the Sun's gravity. Within that sphere, the passage of a small body like 2026 JH2 experiences what planetary scientists call gravitational focusing. Earth's gravity bends the asteroid's path slightly, acting like a subtle but real lens on its heliocentric trajectory. This does not drag the asteroid toward us or turn a safe flyby into a dangerous one. The trajectory remains safe throughout. What gravitational focusing does is produce a small but measurable change in the asteroid's orbital path after it leaves our neighborhood. This is actually scientifically valuable data, because studying how Earth's gravity deflects a known object helps calibrate models of orbital mechanics that are used to predict future close approaches by other objects. During the closest approach, the asteroid will brighten to a peak apparent magnitude of approximately 11.5. That means it will be visible through amateur telescopes under dark sky conditions, a remarkable opportunity for backyard astronomers to watch a city-killer-sized rock swip through the Earth and Moon system in real time. It will move visibly against the background stars as the minutes pass, a slow and ghostly reminder of what is out there in the solar system sharing our orbital neighborhood. Now we come to the scenario that planetary defense scientists use to stress test their models, the hypothetical impact. NASA has confirmed with certainty that 2026 JH2 will not strike Earth, but understanding what would happen if an object exactly like it did is essential knowledge for any civilization that hopes to protect itself from future threats. The first thing to understand about a 25-meter rocky asteroid hitting Earth is that the atmosphere becomes the primary battlefield. Earth's atmosphere is thick and dense enough to act as a genuine shield against objects of this size class. As the asteroid enters at hypervelocity, the air in front of it cannot get out of the way fast enough. The pressure builds to extraordinary levels. The aerodynamic stresses on the rock exceed its material strength, and the body begins to deform, fracture, and ultimately detonate in a phenomenon called an atmospheric airburst. The kinetic energy of the asteroid, which has been building across millions of kilometers of inward travel, is suddenly and violently released into the surrounding air in the form of an explosive shock wave and intense thermal radiation. The total energy release for an object the size of 2026 JH2 is estimated to be equivalent to the detonation of somewhere between 200 and 246 kilotons of TNT. If the asteroid falls at the higher end of its 35-meter size estimate, that yield climbs to a potential 675 kilotons. These numbers are not abstract. A 200 kiloton airburst is a weapon-class energy release. For comparison, the nuclear bomb dropped on Hiroshima in 1945 released approximately 15 kilotons of energy. A 200 to 246 kiloton airburst is 13 to 16 times more energetic than that single detonation, and it happens in the sky over whatever city or region happens to be below it, without any warning, without any countdown, without any evacuation order. The mechanics of that airburst are terrifying in their specificity. The shock wave punches downward and outward from the point of detonation. Structures in the blast zone experience a sudden and violent increase in atmospheric pressure, followed by an equally violent decrease as the wave passes, a combination known as the overpressure and negative pressure cycle. Buildings that survive the initial crush are then torn outward by the negative phase. Glass does not simply crack, it explodes inward and outward simultaneously, turning every window in the affected area into a horizontal hail of razor-sharp shards moving at high speed. The thermal pulse from the airburst radiates intense heat outward from the detonation point, capable of igniting fires, burning exposed skin, and causing flash blindness in observers looking toward the sky. And then there is the noise, a thunderclap so powerful that it can rupture eardrums and collapse internal organs in close proximity to the center. This is not a theoretical damage model. We have a reference event, and it happened within living memory. On February 15, 2013, a stony asteroid approximately 18 to 20 meters in diameter entered Earth's atmosphere over the Chelyabinsk region of Russia. It was traveling at 18.6 kilometers per second, considerably faster than the approach velocity of 2026 JH2. The Chelyabinsk object had a mass of roughly 11 million kilograms and detonated at an altitude of approximately 30 kilometers, releasing an estimated 440 to 500 kilotons of energy. That is roughly 30 times the energy of the Hiroshima bomb. The explosion shattered windows across more than 7,200 buildings in 6 cities. Nearly 1,500 people were injured, the overwhelming majority of them by flying glass from those shattered windows. Structural damage extended across a wide region. Doors were blown off hinges. Plaster fell from ceilings. People were knocked off their feet by the concussive force, and crucially, nobody saw it coming. Not a single telescope on Earth detected the Chelyabinsk object before it hit. It came from the direction of the Sun, which is the single biggest blind spot in every ground-based optical survey network on the planet. Now compare that event to 2026 JH2. The Chelyabinsk object was smaller, between 18 and 20 meters, compared to the estimated 25-meter median for 2026 JH2. Chelyabinsk was also faster, at 18.6 km per second versus 9.17 for JH2. Because kinetic energy scales with the square of velocity, a slower object carries significantly less energy for a given mass, which is why, despite being potentially more massive, JH2 does not necessarily exceed Chelyabinsk in total yield. But the lower bound estimate of 200 kilotons is still an extraordinary amount of destructive energy, and the upper bound of 675 kilotons is worse than anything Chelyabinsk produced. The critical difference is location. Chelyabinsk struck over a sparsely populated region of Russia. The 1,500 injuries were serious, but they did not represent a catastrophic urban disaster. Now place that same airburst over Tokyo, or London, or New York, or Mumbai. The shockwave that broke windows across 6 cities in Siberia sweeps through a landscape of high-rise buildings, subway systems, hospitals, communication infrastructure, and tens of millions of people with nowhere to safely shelter in time. Planetary scientists who study this problem use the term city killer deliberately. It is not hyperbole. It is a technical descriptor for a class of objects that are large enough to destroy urban infrastructure, but small enough to evade detection until it is too late to respond. 2026 JH2 sits squarely in that class. The Moon presents a completely different scenario for a hypothetical impact, one that is scientifically captivating in its own right and carries secondary hazards that extend all the way back to Earth and into cislunar space. Unlike our planet, the Moon has no atmosphere. There is no protective layer of gas to absorb and dissipate the kinetic energy of an incoming asteroid. An object like 2026 JH2 would strike the lunar surface at its full cosmic velocity of 9.17 kilometers per second, transferring every joule of its kinetic energy directly into the Moon's crust and interior. The impact would proceed through 3 distinct stages. The first is the contact and compression stage. The instant the asteroid touches the lunar regolith, an interface of extreme pressure is created between the projectile and the target. Shockwaves propagating through the rock reach pressures of several hundred gigapascals, which is a number so far beyond everyday experience that it requires a different frame of reference entirely. At those pressures, solid rock behaves not like a brittle mineral, but like a fluid. The asteroid itself is instantaneously vaporized. A corresponding volume of lunar rock is vaporized alongside it. What had been solid matter becomes a ball of extremely high-temperature plasma. The second stage is the excavation stage. The energy released by the initial compression propagates outward as a growing shock front that displaces lunar material in all directions. Under the Moon's low surface gravity, which is approximately 1/6 of Earth's gravity, material is lofted more easily and travels farther than it would in an equivalent impact on our planet. A transient cavity, essentially a deep bowl of displaced and shattered rock, rapidly grows outward from the impact point. The final stage is the modification stage, where the walls of that transient cavity collapse under gravity, producing the final crater morphology. Scaling laws applied to the specific parameters of 2026 JH2, its mass, velocity, and the physical properties of the lunar surface suggest that the resulting fresh crater would measure between 300 and 500 meters in diameter and between 60 and 100 meters deep. That is a new crater, visible through telescopes from Earth, appearing on the lunar surface within seconds. The observational signatures of such an event would be extraordinary. The instantaneous conversion of kinetic energy into high-temperature plasma would produce an intense optical flash on the lunar surface. On the Moon's dark side, the unlit portion visible from Earth, this flash would reach an apparent magnitude somewhere between +0.5 and +1.5. That puts it within the range of naked eye visibility for observers on Earth who happen to be watching the Moon at the right moment. It would appear as a brief but brilliantly bright star suddenly igniting on the otherwise dark face of the Moon, lasting for several seconds before fading. Following that initial burst, the pool of impact melt at the center of the fresh crater, potentially 50 meters wide, and heated to temperatures exceeding 2000 Kelvin, would continue radiating strongly in the infrared for hours afterward. Space-based observatories, like the James Webb Space Telescope, could study this thermal afterglow in detail, extracting information about the composition and cooling behavior of molten lunar rock in ways that would directly inform future lunar geology models. The seismic component of the impact is equally significant. Assuming a standard seismic efficiency, meaning the fraction of kinetic energy that gets converted into seismic wave energy, the 200 kiloton impact would inject roughly 86 billion joules into the lunar interior. That is enough to trigger a global moonquake estimated to measure between 3.8 and 4.2 on the Richter scale. The Moon has a unique seismic character. Because it is an ancient, dry, and highly fractured body without the liquid water that dampens seismic activity on Earth, moonquakes ring for extraordinarily long periods. The entire Moon would vibrate for tens of minutes after impact, sending seismic waves propagating through its interior in ways that carry detailed information about the thickness of the crust and the depth of the core mantle boundary. Scientists would effectively receive a free, unprecedented seismic tomography experiment courtesy of a natural impact event. But the lunar scenario also carries dangers that extend far beyond the surface of the Moon itself. The impact of 2026 JH2 would loft an estimated 20 million kilograms of pulverized lunar rock and fine regolith dust into space. Some of that ejecta would simply ballistically follow suborbital arcs and land near the crater, forming an ejecta blanket of secondary craters and debris extending up to a kilometer from the impact site. But the lighter, finer particles, the micron-sized dust grains and small rocky fragments, would be launched at velocities exceeding the lunar escape speed of 2.4 kilometers per second. Those particles would disperse through cislunar space, the region of space between Earth and the Moon that is now increasingly populated with operational satellites, communication infrastructure, navigation systems, and planned future crewed facilities. Lunar dust is not a gentle substance. It is highly abrasive, electrostatically charged, and irregular in shape at the microscopic level. Even a tiny grain of it, traveling at orbital velocities, carries enough energy to pit a solar panel, scratch an optical sensor, or compromise a thermal radiator. A cloud of 20 million kilograms of this material moving through cislunar space represents a serious and sustained hazard to every asset operating in that region. Furthermore, if the impact happened to strike the leading hemisphere of the Moon, the face that always points toward Earth, a fraction of the high-velocity ejector could be directed on trajectories that intercept Earth. Days or weeks after the impact, that material would enter Earth's atmosphere as an unusual and localized meteor shower. Unlike the familiar meteor showers driven by cometary debris, which consist of icy particles and fragile dust, this shower would be composed of stony silicate grains blasted from the lunar crust. Atmospheric scientists would have an extraordinary opportunity to analyze lunar crustal composition directly by studying the spectral emission lines of those incinerated fragments as they burned up overhead. All of which brings us back to the question that sits beneath every piece of this story. What does the existence and the close flyby of 2026 JH2 tell us about the state of our planetary defense capability, and are we actually prepared for the version of this story that does not end with a safe flyby? The answer begins with a number: 8 days. That is how long humanity had between first detecting 2026 JH2 and watching it sweep through the Earth and Moon system. 8 days from discovery to closest approach. In the context of everything we know about asteroid deflection and planetary defense, 8 days is essentially zero. The most successful asteroid deflection ever executed was NASA's double asteroid redirection test, the DART mission. In September 2022, a spacecraft deliberately impacted the moonlet Dimorphos in the binary asteroid system Didymos and successfully changed its orbital period by about 33 minutes. That was an extraordinary achievement, proof that kinetic impactor technology actually works in practice, not just in simulation. But the DART mission was the product of years of design, manufacturing, testing, and launch operations. It required a precise launch window calculated far in advance. It required months of interplanetary crews to reach its target. It required detailed characterization of Dimorphos before the final approach. None of that is possible in 8 days. Even the most aggressive theoretical fast response scenario, deploying a standing interceptor mission that was pre-designed, pre-built, and ready to launch on short notice, would require at minimum weeks to months to execute a useful deflection against a known impact trajectory. For objects much larger than JH2, a nuclear standoff detonation represents the most viable last resort option, capable of delivering enormous energy at a distance without requiring a precision physical impact. But even that strategy, which exists at the edge of international treaty law and requires significant political coordination, has never been tested in practice and demands preparation timescales far beyond 8 days. What 8 days actually buys you in planetary defense is the time to calculate where an asteroid is going to hit, define the damage footprint, and initiate emergency evacuation. That is it. That is the entire operational portfolio available to civil defense authorities in a scenario like this one. And evacuation, while absolutely preferable to no response at all, has its own catastrophic limitations when applied to densely populated urban areas. Moving millions of people out of a major city in days requires extraordinary infrastructure, flawless communication, and a public that immediately understands and responds to the threat. History does not particularly encourage optimism on any of those fronts. The reason 2026 JH2 was not discovered earlier is not a failure of any particular observatory or scientist. It is a consequence of physics and the fundamental limitations of ground-based optical astronomy. Small near-Earth objects in the 20 to 40 meter size range have extremely low absolute magnitudes. They reflect very little light. They are essentially invisible against the background of deep space until they move into the relatively close vicinity of Earth. Ground-based telescopes are also constrained by weather, by the day and night cycle, and most critically, by the same blind spot that hid the Chelyabinsk impactor from every telescope on the planet. If an asteroid approaches from the direction of the Sun, ground-based optical surveys simply cannot see it. The Sun's overwhelming brightness drowns out any nearby faint object during daylight hours, and by the time an asteroid approaching from that direction moves into observable night sky geometry, it may already be days or hours from impact. The solution that the planetary science community is actively advocating for is the deployment of dedicated space-based infrared telescopes positioned where ground-based systems cannot reach. The Near-Earth Object Surveyor, known as NEO Surveyor, is a mission designed specifically to address this gap. Positioned at the Sun-Earth L1 Lagrange point, which is approximately 1.5 million kilometers from Earth toward the Sun, NEO Surveyor would operate continuously in infrared wavelengths, detecting the thermal emission of asteroids rather than relying on reflected visible sunlight. This is a crucial distinction. Because asteroids absorb solar energy and re-emit it as heat, an infrared telescope can detect them regardless of their albedo, regardless of their size class, and regardless of whether they are approaching from the sunward direction. NEO Surveyor would also operate free of atmospheric interference, weather delays, and the day and night cycle that ground-based systems must work around. The science case for this kind of space-based survey is overwhelming. The discovery of 2026 JH2 with just 8 days of warning is not an anomaly. It is representative of a systematic gap in our current detection capability for objects in this size range. There is an undetected population of city-killer-class asteroids in the inner solar system, objects that are large enough to cause devastating urban destruction, but small enough to remain invisible to our current surveys until they close to within days of Earth. The exact size of that undetected population is, by definition, uncertain, but population models developed by planetary scientists suggest that a substantial fraction of objects in the 20 to 50 meter range remain uncatalogued. Each one of them is 2026 JH2 waiting to be found, or waiting not to be found until it is too late. The close approach of 2026 JH2 to within 24% of the lunar distance is an event that deserves more attention than it typically receives in the daily flow of news. It is not a near miss in the dramatic Hollywood sense. The asteroid was never going to hit us, and the trajectory was never uncertain enough to generate serious alarm in the planetary science community. But that is precisely what makes it such a powerful case study. Here was a real, verifiably tracked object with enough kinetic energy to vaporize a city block, level surrounding structures across an urban area, shatter windows across a metropolitan region, and injure or kill thousands of people, sweeping through the Earth and Moon system at 9 kilometers per second, visible to telescopes, catalogued in the databases, and yet detected just 8 days before it arrived. If its orbital parameters had been slightly different, if the perihelion had been a few thousand kilometers closer to Earth, if the geometry of the Sun-Earth encounter had placed it on an intersecting path, the only thing standing between that energy release and a city would have been the time it took authorities to calculate an impact zone and order an evacuation that may or may not have been fast enough to succeed. That is where planetary defense currently stands. The science is advancing. The technology is being developed. The missions are being designed. But the gap between what we can currently detect and what is actually out there remains real and significant. The message, written across the trajectory of 2026 JH2, is not one of doom or inevitability. It is a message about urgency. It is a reminder that the solar system is not static, that the inner solar system is populated with fast-moving objects that carry devastating energy, and that the difference between a safe flyby and a catastrophic impact can come down to an orbital difference measured in tens of thousands of kilometers. Funding: NEO Surveyor. Expanding ground-based survey networks. Developing rapid response deflection capabilities. Building international frameworks for civil defense coordination. These are not optional luxury investments in the distant future of space science. They are the practical requirements for a planet that intends to still be here in the centuries and millennia ahead. 2026 JH2 swept through the Earth and Moon system, reached its closest point at just 91,000 kilometers from our surface, and continued on its way around the Sun without incident. The next one might not be so polite. If you found this as important as I do, leave a like on this video and subscribe to the channel so you never miss a story from the universe that actually matters.